Hello students, in continuation with my lecture series for AKTU Engineering, Energy Science and Engineering, I am continuing with Unit 1, Lecture 3. Don't forget to subscribe my channel, and the Word file of whatever I am teaching is available in the comment section below my YouTube video. Also, the book is available on Amazon. You can find the link for the same. Okay, now in my first two lectures of Unit 1, I briefed you about the types of energies. Then I explained you Schrodinger wave equation, time dependent, time independent, then the conditions necessary for acceptable wave function. Now, today we are going to study particle in one-dimensional well using Schrodinger equation. This is very, very, very important Unit 1 question. It will be asked in the paper, either in the form of a numerical it will come, or you will have to derive an expression for wave function for a particle which is trapped in one-dimensional potential well. It is very easy. Just follow me step by step. Now see, firstly, what will be the question? Write Schrodinger's wave equation for a particle in one-dimensional box or well and solve it to obtain the eigen values and eigen functions. Okay, wave equation for one-dimensional particle in a box. Very important. 10-mark question. Whole derivation will be there. Now look at this diagram here. What do you mean by the word well? Well, that is in Hindi kuan, the length will be very long or many more times compared to the breadth. So see, here look at this diagram. The length is long and the breadth is small. And for our convenience, because we are going to use Schrodinger wave equation to solve this, we will assume that potential inside the well is 0 and outside is infinity. Also, our x dimension limits will be x equal to 0 and x equal to L. Here length L. Also, probability of finding that particle is 100% inside the well and totally 0 outside the well. And now what have I got to do? We have to find a wave equation for a particle which has trapped in this condition inside a well, and also the energy levels, that is the eigenvalue of energy for n equal to 1, n equal to 2, n equal to 3. What will be the position of the particle? So basically this is like some mathematical numerical you have been given. You have been told the limits and now you have to start solving this mathematical expression. So let us begin. See, a particle has been trapped in the box with infinitely hard walls. The motion of the particle is specific along the x-axis between x equal to 0 and x equal to L. The potential energy of the particle is infinite on both the sides of the box, and V is constant, say 0 for convenience inside the box. Now the particle, we have to find the equation for this wave expression between x equal to 0 and x equal to L. We will take up the Schrodinger wave equation del 2 phi by del x2 plus 2m upon h bar square into E minus V phi equal to 0. Now here in this case, we have been given V equal to 0. So we will put V equal to 0 here and the expression reduces to del 2 phi by del x2 plus 2m upon h bar E phi equal to 0. Now, this is a two-dimensional equation. As per mathematical concepts, the general solution for the wave expression will be of this form. Phi equal to A sine under root 2 me upon h bar x plus B cos under root 2 me h bar x. This comes from mathematics concepts of differential equation, where it is a two-dimensional differential expression and it has a general solution in this form. This is mathematics. Now, A and B, these two constants, we are going to evaluate and find out the expression, wave expression for particle trapped in one-dimensional well. So we will solve it like we are doing mathematics. So first we will simplify this equation a bit more. We will apply the boundary conditions for phi equal to 0, for x equal to 0 and x equal to L. When I will put x equal to 0, it will all reduce to 0. Now let me put x equal to L. So for x equal to L, cos theta will become 1. The second term then cannot describe the particle because it is not vanishing at x equal to 0. It is showing some value. So after applying my boundary conditions, phi will be 0 at x equal to 0 only when under root 2 me upon h bar L is equal to n times of pi. Then what is going to happen? Your wave equation phi will become 0. This is basically for the sine values. Why? Because cos 90 or the maxima is, cos 0 is 1. So this is not reducing to 0, but sine 0 is 0. It is reducing to 0. So we will take the limits for this expression, sine under root 2 me upon h bar equal to n pi. Now, energy of the particle can have only certain values which are known as Eigen values, and the expression for them is given by En is equal to n square pi square h bar square upon 2 ml square, where n is 1, 2, 3 and so on. So wave function of particle in a box whose energy is En is given by phi equal to A sine under root 2 m En upon h bar into x. How did we get this expression? We have got it from here, and we have left out this expression because this is not satisfying my boundary condition. For x equal to 0, this is not coming 0, this is coming 1. So I am only taking the sine term. So here my expression is. In this expression, I will put the value of En from here, and I will get phi n is equal to A sine under root, after putting En equal to n square pi square h bar square upon 2 ml square, A sine under root n pi x by L. Here phi n is eigen function corresponding to the energy eigenvalues. For each quantum number n, phi n is going, if it has to be acceptable, then it should be single valued, it should be finite, it should be normalized, and it should be continuous. So I will integrate this over the whole space from x equal to 0 to x equal to L, which are my limits here. X equal to 0 to x equal to L is equal to a square integral 0 to L sine square n pi x by L dx will be equal to 1. This is the expression for normalized wave equation here. Phi n square dx should reduce to 1 for the condition of normalization, and phi n is this. So its square comes out as this. Now we will use the formula cos 2 theta is equal to 1 minus sine square theta, and I get this expression like this. After I integrate, cos theta becomes sine theta divided by this constant. I will put the limits from 0 to L here. equal to normalized wave function value, and on solving I get A equal to under root 2 upon capital L. Normalized wave function of the particle comes out as phi n equal to under root 2 upon L sine n pi x by L, where n is 1, 2, 3, etc. This is an expression for normalized wave function for particle trapped in one-dimensional box or well. It is important and it is asked. How did I do? I wrote the equation for wave function. I used the condition of normalization, which is mod of phi n square should be equal to 1. I equated it to 1. I used the formula of cos 2 theta and I integrated this expression. So integral cos theta is equal to sine theta. That formula I used. Then I put the limit from 0 to L for x, and on solving I got A equal to under root 2 upon L. This has been asked. Now look here. For n equal to 1, n equal to 2, n equal to 3, that means they are eigen values. That is n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, etc. So this is the eigenvalue or the eigenfunctions. This numerical has been asked twice or thrice since the time this paper came in your syllabus. Let us quickly solve it. Find the probability that a particle is trapped in the box between 0.45 L and 0.55 L for ground state and first excited state. That means you have to take n equal to 1 and n equal to 2. Now, from the above derivation, we know that phi n is equal to under root 2 upon L sine n pi x by L. The probability of finding the particle from my condition of normalization comes out as mod phi n square dx should become equal to 1. So integral x1 to x2. What is x1 and x2 has been given to me in the numerical, and I know cos theta is equal to cos 2 theta is cos square theta minus sine square theta. So probability comes out as 2 upon L into integral x1 x2 half into 1 minus cos 2 theta 2 pi nx by L into dx. I have put this value instead of sine square theta. Okay, so cos 2 theta is this much, the basic trigonometrical formula. And then probability of finding the particle, this formula, I will integrate it here. Cos integral becomes sine, and the probability of finding this is between x equal to 0.45 to x equal to 0.55. So this is sine, not sine square. The ground state n equal to 1, we get the values as, we put these values, and after solving using sine A minus sine B equal to 2 cos A plus B by 2 into sine A plus B by 2, we get this value. From calculator, we solve it, we get the answer as approximately 19.8%. For n equal to 2, this will become 0.65%. A particle is moving in one-dimensional potential box of width 25 angstrom. Calculate the probability of finding the particle within an interval of 5 angstrom at the center of the box when it is in its state of least energy. Least energy will be in n equal to 1. And I know from my concepts that phi is equal to under root 2 upon L sine n pi x by L, or A in this case we have put. So for n equal to 1, this expression becomes pi x is equal to under root 2 upon A sine pi x by A. At the center of the box, x is equal to A by 2 because the whole distance is A. If you will take the center or half, it will become A by 2. So probability of finding the particle from this to this dimension becomes under root 2 by A sine pi A by 2 here. Instead of x, I have put A by 2 whole square, and on solving you get the answer. An electron is bound in one-dimensional potential box which has a width of 22.5 into 10 to the power of minus 10 meter, assuming the height of box to be infinite. Calculate the lowest two permitted energy values of the electron. We know from the formula for Eigen values, En is equal to n square h square upon 8 ml square. H is Planck's constant, 6.6 into 10 to the power of minus 34 joules second. Mass for electron is 9.1 into 10 to the power of minus 31 kg, and L has been given to me as 22.5 into 10 to the power of minus 10 meter. I will put these values here. I have been given lowest two permitted values. So n equal to 1 and n equal to 2. I will get the answer. Now, energy in chemical systems and processes. That means where all are, can you see the direct results of energy in chemistry, chemical reactions. If you keep milk in scorching heat, it will because of various chemical processes it will undergo, because of the energy from the sun, it will change its form and not be left for utilization. So chemical energy is also very important if we are studying energy science and engineering. We should be knowing about exothermic reactions and endothermic reactions, because chemical reactions happen because of the bonds between atoms in the reactants and molecules. It is happening on the nuclear level. So it is very important. Exothermic reactions are reactions or processes that release energy, usually in the form of heat or light. And exothermic energy, the reaction energy is released because total energy of the products is less than the total energy of the reaction. And here are the reactants, here are the products. Take the example of milk. It has been kept in heating sunlight. So they are the reactants. They will get activated in heated sunlight, and the products we will get when we keep it in scorching heat. So the energy in exothermic reaction, enthalpy change becomes negative, and you can take any simple formula. For example, hydrogen is burning, so hydrogen and oxygen results in water. Other examples, combustion, combining strong acids and bases. Endothermic reactions are chemical reactions in which the reactants absorb heat energy from the surroundings to form products. The reactants lower the temperature of their surrounding area, thereby creating a cooling effect. Photosynthesis has been asked in section A twice. Define photosynthesis. You all must be familiar with this word photosynthesis. Already must have heard it in biology also. Photosynthesis requires energy to drive the chemical reaction. Photosynthesis is an endothermic reaction. This means it cannot occur without the sunlight. It happens in day. Plants absorb energy from sunlight. Their leaves, they change carbon dioxide to, and they release oxygen in the environment. Few plants do it also at night, especially the oxygen loving plants like neem, aloe vera, etc. But generally it happens in sunlight, and the required light is absorbed by green pigment called chlorophyll in the leaves. Fuel cells, they are also part of chemistry. What are they doing? They are taking chemical energy of hydrogen or any other fuel and producing electricity. If hydrogen is the fuel, then electricity, water, and heat will be the only products. Fuel cells are unique in terms of variety of their potential applications. They can provide power for systems as large as the power station, or they can even give you use their energy for laptops. Fuel cells have wide range of applications like transportation, material handling, etc. For emergency backup of power applications, fuel cells operate at very high frequency. Now there are many types of fuel cells, especially the hydrogen atoms enter the fuel cell at anode, where chemical reaction strips them of their electrons. The hydrogen atoms are now ionized and they carry a positive electrical charge. The negatively charged electrons provide the current through the wires to do the work. If alternating current is needed, the DC output of fuel cell must be routed through a conversion device called an inverter. Now, many types of fuel cells are there. I have discussed 3 cases in detail, which you are familiar with in your day-to-day life, usually using hydrogen or oxygen or a solid state material. So simple fuel cell, you must have used it in the lab, which consists of an electrolyte, which consists of an anode and a cathode. That I will discuss with you, the simple one, the alkali fuel cell. It can operate on compressed hydrogen and oxygen. They generally use a solution of potassium hydroxide in water as their electrolyte. And efficiency, you must have seen this type of fuel cell in the lab also, consisting of anode, cathode, and electrolyte. Their efficiency is round about 70%. They can operate at higher temperatures. Output is around 300 watts to 5 kilowatts also. And they are used in spacecrafts, etc., to provide electricity. Now, problem is that they require hydrogen only for their fuel element. Now, molten, and the biggest problem is the electrolyte is a liquid. So at times in aircrafts, etc., it can leak. Molten carbonate fuel cells, they use high temperature compounds of salt like sodium or magnesium carbonates as the electrolyte. Their efficiency ranges from 60 to 80%, and operating temperature is about 650 degrees Celsius. The high temperature limits damage from carbon monoxide, poisoning of cell, and waste heat can be recycled to make additional electricity. Proton exchange membrane fuel cells work with a polymer electrolyte. Polymers are very common in chemistry, and polymers are thin and light, so in the form of a thin permeable sheet. Efficiency is around 40 to 50%. Operating temperature is around 80 degrees centigrade, and their output is around 50 to 250 kilowatt. Solid oxide fuel cells use hard ceramic compound of metal like calcium or zirconium as oxides as electrolyte. Efficiency is 60%. Operating temperatures now will become high because this is solid. So 1000 to 1800. So quickly, types of fuel cells I will remember for my exam: anode, cathode, electrolyte. So that comes under alkali fuel cells. Carbonate fuel cells, approximately the diagram is same, only my electrolyte and the salt compounds change. My proton exchange is using polymer as the electrolyte, which is thin, and the solid state one is using hard ceramic compound, and solid will be having the highest temperature variation. Flow of carbon dioxide. This is also chemical energy, very, very, very important. Every year, flow of carbon dioxide, 10-mark question has been asked. So first, understand this diagram. If you are able to make this diagram in your 10-mark answer, you will easily score marks in this. It is simple, very simple process which is happening day to day in our lives. So please, flow of carbon dioxide, very, very, very important. Carbon cycle is the process where carbon compounds are interchanged among the biosphere, geosphere, hydrosphere, and atmosphere of the earth. Carbon dioxide cycle basically can be divided into 4-5 steps. Carbon present in the atmosphere will be absorbed by the plants. This is known as photosynthesis, and it is a chemical process. These plants, which are consumed by animals, and carbon gets bioaccumulated in their bodies. These animals and plants die eventually, and with time, upon decomposing, this carbon is released back into the atmosphere. Some of the carbon that is not released back into the atmosphere comes back as fossil fuel. These fossil fuels are then used for human activities, which pumps more carbon back into the atmosphere. Now look at the example. Suppose this is any animal, like in this diagram, you can see a cow standing. It is respirating, that is inhaling oxygen and exhaling carbon dioxide. Ultimately, this carbon dioxide is going back into the atmosphere, and plants are absorbing this carbon dioxide in the presence of sunlight, which is the source of all energy in the atmosphere. And also the decay organisms, etc., the dead organisms and waste products, which are turning into fossils and fossil fuels, root respiratory problems, etc. And ultimately what happens is they are released back into the atmosphere. Factories, etc., are also emitting out carbon dioxide. Photosynthesis process changes this carbon dioxide into oxygen so that a human life can survive on the earth. When these animals, etc., are dead, they reach the earth as dead organisms, and the fossils and the fossil fuels they create are releasing again this carbon dioxide back into the atmosphere, and some of it is getting mixed up with the soil, causing fossil fuel. So carbon cycle on land, carbon in the atmosphere is present in the form of carbon dioxide. Carbon enters the atmosphere through natural processes such as respiration and industrial application. Respiration and industrial application, burning of these fossil fuels when they are burnt in forest, etc., and process of photosynthesis involves the absorption of this carbon dioxide and converts it into oxygen. And carbon compounds are passed along the food chain from producers to consumers. The carbon cycle is disturbed, it will result in serious consequences such as global warming and climatic changes. This is there in Unit 5 of your syllabus. Next lecture, entropy and further. Thank you.